All right, guys, welcome back. In this video, we're going to continue looking at the Biot-Savart law. So in part one of the video previously, we looked at the magnetic field due to a small segment of wire. In part two, we're going to look at another form of this formula, right? So remember, we always start with this main form of the Biot-Savart law, but what we're going to do now is we're going to apply this to a long wire, but a long wire that is shaped into a circular arc, okay? So this is important because it actually has some really nice properties. We can see here, when I have a wire that is completely straight, then I have magnetic field that is being generated along the length of that wire, but radially kind of in concentric circles outwards, right? But if I were to take this wire and bend it into a circular arc, what happens, if you can kind of see here, inside the wire, kind of towards some center of the circle, all of my magnetic field contributions, they're all sort of adding together, right? So by doing this, I have, if I were to get the magnetic field, let's say at this point right here, okay, if I were to look at this, then I actually have contributions from each length of the wire, okay, to that point. But this is kind of mathematically a little bit easier to deal with than in the first case when we were trying to, let's say, find all of the contributions from different lengths of wire up to a single point. The reason for this is that all of these are going to share the same radius value, right? It's going to be kind of a circle. So I don't have different radius values. My radius will become a constant. And this is actually very nice for us. So let's kind of look at what this formula is, and then we'll do another example just like in part one. And remember, this is again for a circular arc of wire. This is the form of this formula, and this is kind of when you apply it. Okay, so we start off with our Biot-Savart law, and here, if I have a circular arc of wire, there's a few kind of metrics that we're going to do. The first is that any length of wire, any arc length of wire, you can calculate how long it is based on the radius and the angle that you go through, right? So this is a little bit of geometry math here that we're doing, that if I want to know kind of the length of a crust of pizza, right, you need to know the radius, right, from the center to the edge, and then what is the angle, right? So what is the angle of that? So you just multiply these two together, r d theta, okay? D theta is the change in this angle from start to end, and that will give me this length of wire. So that's the first substitution we're going to make right here. I'm going to take this r d theta and plug it in for dl. But there's one more step here that we're going to do, right? So this would give me kind of r d theta cross r, right? But there is in this theta cross r, this is the cross product of two things that are perpendicular to each other. They are always perpendicular to each other. If I look at this here, my angle, for example, is going right here. I will draw it as a straight line tangent. And my radius is going this way, so they're perpendicular. Okay, same thing here. Angle is going across this way, radius is going this way. They are always going to be perpendicular all around the circle. And because they are, when I do the cross product of any theta cross r as like unit vectors, okay, then I'm always going to get 1. Okay, so this is very mathematically convenient. This is the kind of, again, leveraging that everything is in a circle. So what this allows me to do is say that this is going to be just r d theta, right? So everything else is going to be times 1. So what I have here is going to be r d theta, my current times r d theta divided by r squared, but now r is a constant. It's not something that I'm integrating. So I can cancel, let's say, the r on the top with one of the r's in the denominator, and then I can take the r out of the integral. I can take the I out of the integral, right? The only thing left in my integral will be, if I look at this, will be my d theta. So if you take the integral of just d theta, then you get theta, right? So this is pretty neat. So I can reduce my entire integral just to one variable. So this is pretty neat. So now I have a new form of this formula that I'm going to leave as mu naught over 4 pi. This is kind of a term that you're going to see a lot. And then I times theta times r, where theta is the angle that you're moving through, r is the radius of that circle, okay, and I is the current in the wire. So let's go ahead and try this. We're going to go ahead and put this into practice with an example right here that looks kind of a little bit fancy, right? So I'm going to take this arc. I think that these are pretty good because they give you some challenge. What we're going to do here is I want to know what the magnetic field is at point P. Magnetic field at point P. So right here, due to this loop of wire. So this is not a circle, right? This might look a little strange because it's not a circle. It's sort of some kind of rainbow arch shape, right? Outline. But if we take just pieces of it, then what you'll see here is that this part right here is a circle, and this part right here is circular. I should say circular. Okay, with P being the center of those circles. If I were to draw this out, we can kind of do this. Draw out a circle here, and if I can sort of match it up, you'll see that P is at the center of some circle with the length A of the wire, and then there's another circle due to the outside, and P is at the center of that circle as well. The only thing really that doesn't fit, okay, is going to be this little segment here, C, and this little segment here that I'm calling D. So we'll deal with those in a little bit. But what I want to focus on right now first is going to be portion A, okay, and portion B. So for portion A, I'm going to call this BA. Let's do this here for BA. This is going to be, let's go ahead and try to set up this formula, the formula to solve this. Now this seems a little bit strange because we don't have values here to plug in. It's going to be more using variables to kind of set up a solution. So let's see what we can plug in. So first we have our constants. This is fine. Mu naught over 4 pi. This is okay. And I know that I have a current I. My current is I. Whatever it is, we're just going to leave it as I. So this could kind of work for any current they want to plug in. So this is going to be times I. And then I have two values here that I need to fill in. My angle and my radius. So see if you can fill in what these should be. At least your radius. You should be able to fill in what this value is in terms of variables in your problem. So let's see. Hopefully you were able to figure this out. If not, kind of pause and take a moment to think about it. But here I have a small circle with P at the center, and my radius from center to edge is A for segment A. So here I have something, right? We haven't put the theta in yet, but I have something, and for R, I'm going to put A. The value is A. Okay. Now, for the angle here, what is the angle of half a circle in radians, right? So we're going to do kind of in radians. So angle in radians. So if I know that a full circle, right, all the way around, that's a little ugly, but we'll do a full circle, kind of measured like this. This is 360 degrees, which is 2 pi radians, right? So we're going to be working with radians here, 2 pi. So if I just have half of this, so if I want to do just half of a circle, then this should be pi radians, right? Just half of it. So that's what we'll do here. We'll put in here my angle. If I start from one end to the other, I should go through half of a circle, which is pi radians. So pi here. So that's one of the only changes here, is that for our angle, we're going to be using we're going to be using radians instead of degrees. Okay. Now that we have our values, you can kind of set this up. And the way I'm going to set this up is I'm going to put, you'll see kind of right now. So what we can do is we can cancel pi and pi, right? And I'll have here mu naught over 4 times I. I'm going to put all of those together. and then I'm going to multiply this by 1 over A. I'll show you in a little bit why we're doing this. Now, this is fine for the magnitude. The last thing here that we need is the direction, right? So what is the direction of the magnetic field from this wire, okay, from this segment right here? I'll kind of highlight it. From this segment of wire right here, what is the direction of the magnetic field at point P? So this is another important point, right? How we're going to do this. Now, if you remember to use your right-hand rule, I have a wire that is carrying current and it's generating a magnetic field. So see if you can use your right-hand rule. Go ahead and pause now and work this out to see if you can use the right-hand rule to figure out the direction of the field that this wire is creating at this point right here. So try above and below. What should the directions be? Left, right, up, down, into the screen, out of the screen. Go ahead and work this out. And then after this, we'll put a sign to it. Okay, if it's out of the page, we'll put positive. If it's into the page, we'll put negative. Okay, so hopefully you're able to do this. So for this segment of wire right here, I have my current moving from right to left. So what you'll do for this right-hand rule is you'll take your thumb pointing from right to left, and then you'll curl your fingers around the wire as if you were grabbing the wire. This is the magnetic field that you make, right? So if I were to draw this out here as, a wire that has some current, then my magnetic field looks like kind of like this, right? Sorry, this should be sort of behind, but yeah, this could look a little confusing, but in here at the top, I should be going into the page. So I'll put X's, and then underneath the wire, I should put dots that's coming out of the page. So I'll label it here on the bottom. So dots here being out of the page, X's being into the page, okay? But your fingers should curl around the wire in this way, right? So this would be the same thing here. If I were to draw this out, I have X's above the wire, dots below the wire. And the thing here is that once I've seen this, then I can follow this out with dots all the way to point P. So point P is going to continue dots. Everything inside the circle is going to be dots. Everything outside is going to be X's. So everything is going to be out of the page. Okay, the magnetic field is going to be out of the page for segment A. So this is positive. So if I want to add this on to my answer here, I will add a positive sign. It's going to be a positive sign due to these dots, right? Okay. Now, I'm going to leave this up to you guys to solve for segment B. So for segment B, can you do the same thing? Okay. So go ahead, pause the video, and see if you can work through this out now. All right, so for this segment of wire, what we have here is going to be very similar, right? We're going to have essentially mu naught over 4 pi times I times pi again, because it's still half of a circle. Okay, it's just bigger. And the only thing really that's changed here is that my radius is now B. Okay, so this is for the setup. This is just for the magnitude. We still need to add the sign, if any, here for the direction of the magnetic field. Okay, so we have this, and again, we're going to mu naught over 4 because these cancel, right? And I have times I, so we're going to put all this together, times 1 over B, right? So again, we just did the same sort of factoring out that we did before, but big difference here is that when you do your right-hand rule for B, okay, your thumb is going to be going from left to right now. So if you curl your fingers, you should be curling your fingers the other way due to this right here, right? Due to this right here. So let's go ahead and color this actually with a different color here. Color this purple so that we know that because of this, my field above the wire is going to be out of the screen, and my field below the wire is going to be into the screen, and this continues all the way, right? Anything inside the circle due to part B is going to be into the screen, including point P. So this means that this is going to be into the page or into the screen, which is negative, which is going to be negative here, right? So negative. So these come from these. Hopefully the color coding kind of helps us to remember. Okay. Now the last thing here, just as a quick to close this out, I have for this wire, I do have two little segments right here. One is C and one is D. And so it's important here just to look at what are the contributions from C and D. But just so we know here that P is on the axis of C and D, okay? So it's kind of parallel to the wire and on the axis is important. So because these are in the same direction as P and P is like in line with them, if I had some point P here, there's no magnetic field along the wire. Remember, I have to be at some point, you know, out here, I'll call this kind of X. I have to be at some point with some radius away from the wire. If I'm on the axis here, this is kind of undefined, for there's no magnetic field here. So it's 0. So these are going to be 0. So if I wanted to add this into the problem, I would have, you know, BC and BD, right? Both of them, I should put, you know, and here, they should both be 0. So what you do for this problem, for the total magnetic field, so, you know, looking for the total magnetic field at point P, what I need to do here will be to take, so I'm going to call this B total, and this should be the segment A, segment B, and then here you can put, of course, segment D, C, and D, right? Of course, with both of these being 0, so you only have segment A and segment B, you'll combine these together. Now be mindful when you do this that segment BA is going to be positive. So I'm going to write this out here. Segment BA is going to be positive, makes it a little smaller, and segment BB is going to be negative, right? So when you put them together, even though you're adding them, but one is negative, so they're going to, you know, subtract from each other. Okay, so your answer will look something like this, and you can see that I have two like terms here, so you could actually factor this out. You could do this here to get a nice answer there at the end. There's our example here for magnetic field that is due to two circular arcs of wire.